Hello, everybody. I'm Daniel Hamilton. I'm the Sustainability Manager for the City of Oakland. And as Anthony mentioned, we were one of the recipients of that second round of EPIC funding to deploy microgrids in ways that helped increase the coordination with local governments and address not only the technical barriers associated with microgrids, but also the governance, the finance models. And what I'm going to present to you today is the result of that. We have submitted the final report to that back to the CEC. Anthony has only about 6,000 pages left to read. Hopefully he'll have comments by the end of the day. Ours was unique among the recipients of this grant in that we looked at existing residential. That is by far what we think is the biggest priority for local governments in dealing with microgrid opportunities, because residential is not only the majority of our load in most of our cities, but in fact, commercial buildings have far easier designs for doing this. They have bigger centralized loads, they have on-site energy management systems, whereas residential, it's all very disaggregated across a bunch of different building types. We're going to get to the commercial buildings, they turn over more quickly, they're just easier targets. Residential is the much harder place to play. So if we're talking about where to invest R&D dollars, we think residential is the place to go. So in Oakland, UC Berkeley, Lawrence Berkeley Lab, Stanford, and NASA worked with the city to come up with the idea of what should a neighborhood look like in 2050 if it's going to meet the city's long-term climate goals of reducing carbon emissions by 83%. That means it has to use about 80% less water than it uses today. It means it has to essentially be functioning as a zero net energy community. It has to have integrated transportation, which also has to be electric. There can be no natural gas on the site. So while this is a microgrid-based project, the design intent is far beyond not only just the microgrid, but also beyond the energy systems. This is energy, this is water, this is food, this is community connectivity, this is local codes, this is finance. Because ultimately, the goal of this is not just to show that it's technically feasible, but to show the pathway by which you could scale this up, not only across Oakland, which there's great potential, but across California and the US. This is what we came up with. Apologize for the scale on these, it's hard, but there's so many details to doing something this ambitious within there. I mentioned that we have microgrid, we did a solar assessment. We're putting rooftop solar everywhere that we can within the south and west facing roofs, tied together with energy storage. We have EV chargers at the curbside for this, along with efficiency within the homes and complete replacement of water systems in there for water efficiency. Water is not a huge energy driver here in the Bay Area, but it is across many other areas. So we thought it was a pretty critical part of this, but also dealing with the recurring changes in water patterns for the drought cycle associated with climate change. This is going to be really important moving forward. It's best to integrate it now while we can. So infrastructure improvements along with this, and I'll explain as we go along just how many things don't work for doing this type of development. And there are many, which we think spurred the need for exactly this type of investment by the CEC in this. So this is what we started with on the site. This is a schematic of the high voltage and low voltage power lines in the area. We like to think that we couldn't have picked a worse spot to do this. This is in North Oakland neighborhood of Golden Gate. This is right along the border of Oakland, Berkeley, and Emeryville. For those of you who don't know, this is about 2 blocks west of San Pablo. So if you're driving through there. We have 4 different connection points to PG&E. You ever try to do a microgrid out of 4 separate connection points off small residential lines, you will find that it is virtually impossible to do. This is all by design, by the way. We were trying to pick a bad neighborhood to show that it's easier to do than whatever we come up with in here. That was a design criteria of the team, and saying that if we put it in a nice newer area with good infrastructure, it would only show where we could do it in nice areas with good infrastructure. We picked this neighborhood because it's low income. We picked it because it has bad infrastructure, and because we think it represents the worst case scenario, and we can still make it, do an evaluation here that shows if it's the right scale of solution. So it's just a mess. We've got 28 properties in here, 26 single family homes, 2 apartment buildings. Almost all of the single family homes have been subdivided into 2 or 3 or 4 units. So not only do we have an array of buildings, mostly built around 1910 or so, but we also have a wide variety of tenants, property owners who don't necessarily live in the area, as well as at least 2 houses that we couldn't go in because the police department told us what was happening in the houses. Work that into your engagement strategy. So we started by doing a rooftop solar generation analysis. Result of this, we came up with 364 kW of DC power and solar potential. Off that, we could generate about 509,000 kilowatt hours a year off of that. So that was our energy budget to start with on solar. We had to get everything else down to that number if we wanted to power this whole thing with rooftop solar. Because we were going to do storage on site, this is roughly our budget. But not only do we have to offset the electricity load, we have to offset the gas load and the vehicle load with that too. It was a very challenging energy budget, but the good folks at the Lawrence Berkeley Lab were up to the challenge. So we went in and modeled each one of the homes. We started with 587,000 kilowatt hours of electricity plus the equivalent energy if we were to switch the gas systems over. It does not include the transportation. We had to add that on. When we got done with all of the efficiency within the homes and the fuel switching, we got it down to 357,000 kilowatt hours. So you can see we got about a 40% reduction in total energy use, and that's inclusive of all the fuel switching within there. So that's about the scale of efficiency that we're talking about within the homes. We did this by getting to virtually every system within the house. All electric replacement of the old appliances, comprehensive lighting updates, but we had to do the envelope to do this, not just attic and subfloor insulation. We have to get into the walls. So we have to do, most of these homes have no insulation within the walls. The wall cavities are going to allow us to either, if they have really bad siding, we can pull off the siding and go in from that side. Otherwise, we're going to be doing drilling and blown-in cellulose into the wall cavities. This is what it takes in the retrofits to get the energy budget down to the point where you can use just very small heat pumps to do the space heating. You can see the blue bars represent the original load. The red bars represent the EE package after it's done. So pretty substantial retrofit in virtually every building. This kind of gives you an idea of how this microgrid is intended to work together. All rooftop solar, we don't have anything ground mounted because we're in a residential environment with a lot of trees. We really don't have any other options available to us for this. It includes the street lights, it includes curbside standards for EV charging, and we have 8 EV chargers for shared electric vehicles within the neighborhood. I'm going to get into this in detail later, but you'll see our one little image on here is the first place we realized that if we wanted to do a 2050 neighborhood without, with minimizing the carbon impacts from that, having lithium ion doesn't work. Specifically because lithium ion is a metal that's going to become increasingly scarce over time, and also has a lot of issues associated with not only the upstream impacts from mining lithium and the other metals that go into that, but also in the disposal issues. So at this scale, we looked around at all the technologies. We landed on flywheels. Flywheels are an entirely mechanical storage system. This is 99% steel. You make this, you spin it really, really fast whenever the energy is cheap. You add some friction whenever the energy is expensive. That serves as your battery. You can do about 4 hours at a time off flywheels. So we were able to do this. The batteries are 100% recyclable, but they also have a very long shelf life and no degradation over time. So it's a really remarkable technology for minimizing the carbon footprint of these things, especially as you start to look into the life cycle costs. We don't have enough time in the presentation today to delve into that, but we did life cycle analysis of every component in here. So we're not just looking at the emissions associated with operating these homes in Oakland, but also the upstream impacts of the building materials, the insulation materials, the flywheel storage system, everything that we're putting into this. Are we creating more impact outside of Oakland than we're saving within it? That's a big part of the question that usually goes unanswered in a lot of these things. We did this analysis and it absolutely shaped what type of efficiency we were doing in homes and certainly the choice of the energy storage system. We do have a utility garage for this. One of the many challenges in a residential sector is where do you put everything? Most of these things are privately owned property lots. Nobody wants to give up their own lot for the community systems. We asked, they all said no. So in this case, this neighborhood is next to an industrial corridor on the other side of one of the streets. So we found a lot over there that is a garage. We were able to get rights to that garage to use it so we can do an all-enclosed utility plant, which is good because it does need security associated with it. Anthony mentioned the need for cybersecurity associated with these. These are hackable systems. They are very connected. So we know that security, both physical and electronic, is part of this. So you have to find a way to either put these things in a secure facility or put them underground. In our case, we're doing both. It will look like a storage shed, There will be ancillary equipment up top, and the flywheels will be buried underground in it. Yes, there will be a secret staircase. So here's what we ended up with. Here's the details on what I showed you earlier. About 360 kW of rooftop solar that we can get across these different rooftops within there. The blue loop, we decided to do an exterior loop. We looked at interior spines and exterior spines for getting the power across. We were able to get about 500 megawatt hours a year out of this, and it is sufficient to offset the entire load. One thing I'm not going to cover in detail here, but you see this is DC plus AC microgrid listed on there. One of the big conversations among the truly nerdy of the energy nerds on this is whether or not we should keep this whole thing AC or whether we should convert all these homes to DC power and just give them DC. You could get a tremendous amount of boost if everything ran on DC, because that's what the solar panels are producing the power in. If we didn't have to invert it, we would save a lot of power. Inverters actually cost a fair amount of power on there. So we did 2 design options. Anthony will get to read about both and decide which one is more investable in the future. But we have an option that converts everything to AC, sends it back in a very traditional process. We have a separate design that's a lot more expensive and probably not cost effective, spoiler, that would do a secondary DC grid into the home so that you could run things like stoves, induction stoves, water heaters, heat pumps. You could run all of those on DC. The technologies are already there. If you do those, you could get a lot more efficiency. The power would just come out DC off the solar panels, be stored DC in the flywheels, and be sent out DC directly to the homes. It could be a lot more efficient if you do this, but for it to work at scale, everything has to switch back to DC. We could have a fun Tesla Edison debate about 100 years later, it all switches back. This is what a flywheel looks like. That was one of the main things everybody wanted to do. We wanted to go see these. They're made in Alameda. So this is on the island of Alameda. A company named Ember does these things. Each flywheel is about 40 kW, so 160 kilowatt hours per unit. We scaled up to 3 of them. We actually have room to do up to 10 within the utility garage if we wanted to do more. Part of this, you're seeing this at the block scale, is what we chose to look at for design perspective. But we had some energy systems that said we should be doing these at a 2-block scale. The water systems, we should have been doing it at a 10-block scale. Everything had a different scale at which it is most effective. So that's part of the challenge of this, and the follow-up work to it is, what do you do with this? Is 1 block the right way to go? We looked at that, but there may be more options, and certainly some of the technologies suggested more, including the flywheels can definitely do more than 1 block at a time. So they have no CO2 emissions, they have no capacity degradation, they have no hazardous materials. They're a lovely mechanical solution to this. They are very sensitive, so you do have to install them very, very carefully, but the technology is there and available and manufactured locally, which is important to a lot of your communities. This is just what you could do in Oakland if you scale these up. I mentioned that we wanted to do residential because it's the most difficult and it's more than half of the load within Oakland, but these are considered first ring residential suburbs, the stuff that happened generally between about 1900 and just after World War II and the post-war housing boom within that. About 25% of the housing stock in the United States. Imagine if we had a cost-effective retrofit strategy for 25% of the housing in the United States. I don't know that we came up with the answer to that. I think we did help move it in the right direction as to what technologies might work. But we've got 3,500 EcoBlocks in Oakland that we could do. Not all of them would use these same technologies. We found very specific neighborhood issues and street infrastructure issues that were driving the solutions we came up with. But this is enormous, the potential that you can if you deploy this at scale. I put this slide in there so you could all look at it later in detail at a much better scale. But just to get an idea of how everything works, we did it down to the individual home level. We have this schematic for each of the homes within there down to detail. But lighting, appliances, metering technology, everything on electric. One of the coolest technologies that is not quite market available, we were able to get it, but we were able to get it through a relationship with the manufacturer on this, is integrating all of the heating strategies within the home. Right now, most of you have a water heater in your home and you have a furnace in your home. The same process is happening in both of those things. They're just 2 separate appliances. Integrate them to a heat pump, you can do them together. So almost all of these houses have a hydronic water heating system with a space heating system. So essentially, you have a great big water heater. It runs hot water through a coil over an air handler, and then it blows that into your home. Pretty simple. These aren't manufactured at scale yet, so it's not a scalable technology, but the technology does exist in nascent form. There are 2 manufacturers out there who have demonstration models of it. That's what would be installed here if it's successful in the phase 2 application to build this. At the block scale, you can see sort of where the utility garage is relative to the others and the PG&E grid connection stuff. We were able to condense the grid connections down to a single point in fairly intense negotiations with PG&E, but it comes at a cost, and it's a pretty substantial cost relative to the cost of the whole project. This is the DC version of that same house that you saw earlier. It is quite a bit more complex because you have a redundant DC line going in. You have to do a separate panel at the house to bring in the DC current and then spread everything out. So it requires essentially new circuitry for everything that you want to have on the DC power. If you were going to do this as a new construction model, you could do this as a design capacity from scratch. It's not actually that much more expensive to do. If you want to find out what that looks like, talk to the Santa Rosa folks. They're considering this as part of the rebuild strategy for the fire damaged homes in some of the neighborhoods in Santa Rosa. Same thing at the block scale. You essentially just double the lines that are going in there to each home. You can go in the existing right of way on this. So at the block scale, it doesn't make a big difference, but at the house scale, it really does. I won't read this slide to you, I promise. But this, for those of you who don't want to read our entire gigantic report that we gave to Anthony on this, this is a summary for your take-home slides about what we did for storage, the AC and DC microgrid, the EV charging, and the energy efficiency within each of the homes along with the solar on this. So this just gives you the quick specs on those if you want to see how this works at a scale of something like Oakland and a demand of about 500,000 kilowatt hours a year. It's a lot. But when we're done with this, Z&E is readily achievable in existing inefficient housing. These things have terrible infrastructural, single pane, metal framed windows, no wall insulation within there, bad appliances, low income. We were still able to get all of these homes to Z&E. We didn't necessarily take them all in there in the recommendation. You saw we went about 40% efficiency. We converted everything over to electricity on that, but you're still not going to get to a balanced Z&E. The storage will help with a lot of this. The grid mandate will get you to the backup, but it is not quite a functional Z&E community. It will be in some years. It will not be in other years. The 80% water reduction I didn't get into. It is in the final report, but since this is a microgrid discussion, I've left off the water efficiency. Essentially, we're pulling out all of the water appliances with that. We're doing water metering in it. There are definitely reuse potential, laundry to landscape systems. There's rainwater collection on all of these, so rack-mounted PV above, but we're going to replace the roofs to allow for the water to drain down in a sense that we could use for all of the exterior irrigation. So we'll be reusing toilet water. Potable water will go to gray water will go to black water will go on-site treatment. This is how you keep reusing the water over and over on the site. So we're going to use the toilet water, we're going to use the shower water, we're going to use the rainwater. Every drop of water that falls on the site gets used at least twice. And that's it. Pretty simple.
There is time for questions, and Deborah will be walking around with a microphone. We have 5 minutes, so keep it brief.
Rick Lewis with the Clean Coalition. Awesome project. I actually have a couple of questions that are related. I'm wondering, it sounded like the new electrical loop will be a privately owned. In other words, it won't be PG&E. Is that true?
Yeah, so a big part of the study that's in here is both the local government changes that need to happen to make these neighborhoods work, as well as the regulatory and finance side of things. So we have multiple finance options for this depending on the scenario. The most basic case is the homeowners association is formed on the block. They own this, and it's all done as part of a property tax levy to maintain those systems. So this is similar to a lighting and landscape district for most of you. So there are systems in place to do this as a special district. We also analyzed it being done as a third-party system, independently owned and operated by a large company that would manage this as a third party and charge a surcharge. We have both of those options analyzed.
Excellent. And then my second question is with the EV charging. I saw that they're attached to the street lights, And I'm wondering technically what the voltage is on those. Is it a level 2 or is it level 1? And then I guess that's being paid for by the association.
Yeah, that one's still kind of open-ended at this point. Everything is envisioned as 220 volt level 2 charging on their dual port. We've talked to several of the provider companies about it. There are different models out there, so they could be owned by the community. They could be owned by third-party groups. We've got a wide variety of people interested in EV infrastructure. As you know, you facilitate a lot of these things on there. So it's open-ended within the grant to how those get done, since I don't think that we know quite what cars we would want. Tesla is promoting a program right now where they have 1 port out of 2 in their chargers. So you can do Tesla charging and everybody else charging in some of the same areas. We're looking at those. It sort of depends on what the car share model is that gets used, since the intent for those is not that they'll be private vehicles, but in fact, they'll be a subset of gig car share or some other similar company.
The homes, is it anticipated that they'll also have EV charging for the folks that do have a garage or a driveway? They'll self-charge their own cars in the street, is for pretty much everybody else?
Exactly. It's for the car share. Anybody who wants to do their own vehicle would do standard wiring within their garage or on the exterior of their home as they see fit.
Eric Monterino from Arup. I have a follow-up to what he was asking about the car charging. Did you think about DC charging? I'd assume that you could do DC lighting for the street lights, and if you had 380 volt DC fast charging, you could see that as an option. Just a comment, don't really need much on that. My actual question was about the flywheels. You said that they had 4 hours of energy storage. I was wondering if you were looking at them more to offset the ramping of the duck curve, not so much for powering all the loads at night. Did you plan to use the grid for powering at night, or was there like a staging of the flywheels to continually power the home?
No, the flywheels will be used almost exclusively for the ramp period within there. When I say it's not Z&E, that's what I mean. Functionally, I think Z&E, you'd be able to meet your power demands 24 hours a day. We can't. We'll be pulling grid power at night when there's no solar on these. The flywheel is really to help flatten that duck curve.
Still be Z&E by California's definition, where you can have your energy met during the summer, your generation met during the summer.
Yes, our KWH will balance out across the whole neighborhood. We will definitely be using grid-supplied electricity on the neighborhood even after full deployment of the EcoBlock. And yes, we did look at the DC fast charging as well. The problem is the charging, when we saw most people would be using those, they'd be plugging them in at the same time as our ramp period, and giving them that much power all at once just blows. That 4 hours of storage goes down really fast when you start hooking up cars at 380 volts.
Cito, DNVGL. My question is around community engagement. I'm wondering, I'd like you to tell us a little bit more about how that went and what strategies you used and what the reaction of the residents and homeowners were.
Great question. Poorly. I would say if we had anything to do over again, it was our community engagement strategy. And I hope Tony won't come back and yell at me later, Anthony, for divulging this stuff to you. But we started this by the academic team picking out the block ahead of time, doing a lot of the scenario analysis, bringing it to the community and saying, look what we've done for you. We're government and academics. Trust us. It'll be fine. They didn't trust us. So we ended up having to, I would say, amend our strategy multiple times on engagement to try to get people more involved. People were interested in the topic, but they very much were skeptical of what was being done, because essentially they were being told you're going to get tens to hundreds of thousands of dollars in your home for doing absolutely nothing, all because we are going to make it so. Do you know anybody that would believe that if somebody showed up at their door saying it? So this group still has some healthy skepticism. There's work to be done on getting residents of this block still signed on to this. All of them have seen it. All of them have been involved in multiple meetings. By the end, we were paying them $50 a pop to fill out surveys. That's how we had to go to get engagement. If we had this to do over again, and I think probably the better strategy from the beginning, and there were people arguing for this, is to open this up as a competition. Say that your city is going to be behind doing 1 or 2 or 5 or 10 EcoBlocks, whatever you guys come up with in this, and throw it out there and let the neighborhood groups organize themselves and submit to you why their block should be the ones to get this. If they see that, there's much more of a sense that this is real and that you get homeowner cooperation amongst themselves advocating for it as opposed to you selling the concept to them. So engagement is the area I think we did most poorly on in developing this project, and in the implementation, it's still going to be a struggle to do that. But with these neighborhoods, I think there are good strategies out there from behavior, energy, and climate change folks to do this. If we had followed them a little bit more closely from the beginning, I think we would have ended up with a more uniform acceptance of what was there. But a lot of the improvements within the home were specifically guided by homeowner interests within this. For instance, induction cooking instead of gas cooking is a struggle. Not a lot of people know about induction. So we had to go in and do demonstrations of induction cooking for them to get them involved. But having people be able to pick what goes into their homes, be it stylistic, be it phasing of things, these are important considerations that have nothing to do with the design, but have everything to do with whether or not people want to have this happen in their home and in their neighborhood.
Jim Lutz. Question that's not clear yet is how much of it was implemented? How much hardware got put in?
Yeah, Anthony, how much is going to get put in? Now, Anthony mentioned that this form of EPIC grant is two-tiered. The first tier was for planning and design. So the Energy Commission gave us about $1.5 million for this, and we privately financed about another $1 million off of that. So we spent about $2.5 million doing all of this work to get there. We have an application now in for, it's a competition among all the first rounders to see which the Energy Commission believes hold the most promise, and that is the construction funding for this. So nothing has been built of this. This is simply a design exercise until the second round of funding is decided upon.